Hello, my name is Theresa Stack. I'm an associate professor at Montana Tech in the Safety, Health, and Industrial Hygiene program. And this learning unit will cover analytical methods and how to read them and interpret them for setting up occupational safety and health or industrial hygiene sampling strategies and protocols. It's part of the Master of Science degree in industrial hygiene. I hope you enjoy this learning unit. So the goal of this learning unit is to gain an understanding of NIOSH methods or the systematic requirements that will ensure that your uh, samples, the data that you collect is accurate and precise. And although there are different methods from the EPA and OSHA and different sources, I'm going to stick specifically with NIOSH analytical methods um, just because they're widely used and simple, I believe, to interpret. So one thing that may help you is if you go ahead to the NIOSH website or to our Moodle site and download an analytical method, one of those examples that I put up there. So for example, for silica or formaldehyde, so you can look at it as we're going through the different material. And finally, we'll start to get into the analytical sensitivity and the difference between the lab's ability to detect and quantify material or concentrations of agents in which you send to them. So analytical methods are based on chemistry techniques, and these methods describe how you as an industrial hygienist should collect the sample, and that's based on the accuracy of the lab to perform the data analysis. And so there are lots of other attributes on the cookbook or the analytical method that we'll look at to include both, as I said, the limit of detection and the limit of quantification, as well as the way that you would handle the sample and how many blanks are necessary to ensure accuracy or precision. The NIOSH Manual of Analytical Methods is a collection of air, biological, bioaerosol, and bulk analytical methods developed by NIOSH. There's different levels of their testability. They promote accuracy, sensitivity, and specificity in industrial hygiene analysis, and they're written both for the lab conducting the analysis and the industrial hygienist who is collecting the sample. OSH professionals must ensure that the lab that they're using can perform the analysis based on the method that you're using for sample collection. So it's important to pre-verify with the lab that the method that you selected is one in which that they can run the analysis on. And you can call the lab for that. So here is the website that you can go to by chemical name or chemical number and be able to find the method for which you would like to use. So I will demonstrate a quick example of that. So here I am on the Center for Disease Control and Prevention's National Institute for Occupational Safety and Health's section in the NIOSH Manual of Analytical Methods. And so if I go back to the index, I can search by chemical name. So you see for crystalline silica, there are 1, 2, 3 methods which I can choose to collect my sample. And the method that I choose is based off of how I would like the lab to analyze the results. And so you can see that nomenclature here on the side. And if I clicked on 7500, which is most commonly used in the mining industry, the method appears, and now I can use that to set up my sampling protocol. So you can either search by name or if you know the method number, you can search by number or you can search by cast number as well. So if I went into, I knew I was looking for 7500, I can find the same method that way. So when we pull up the method, we can see the name of the agent that we're sampling for, carbon dioxide. We can see the chemical formula and the molecular weight, which we may use if we need to convert back and forth from parts per million to milligrams per meters cubed. You can also see the method number listed there. This is important, the current revision. When's the last time it was revised? So this was revised in 1994. It means that these OELs are accurate at that time. So you need to be careful when you're looking at the OELs that are listed on the method. They may, in fact, be old. This is also another important feature of the method. It's the evaluation method. So that's how confident is NIOSH that the lab, when following this method, can accurately analyze your results, assuming that you followed the method accurately as well. And there's a full evaluation, which means it's been completely evaluated, partial, and unrelated. And so a full method is preferred over the other two, but as chemicals and methods change, you may use a method that hasn't been fully vetted yet. You can also see the chemical properties listed on the top end of our analytical method. We also have the chemical abstract service number that is listed if you need to reference the chemical that way, and the registry of toxic effects of chemicals, that number is listed as well. As we move further down in the method for sampling, this is what's important for the industrial hygienist. They tell us what type of sampling equipment we should use, what the flow rates are, both minimum and maximum, and we'll take a closer look at that because this helps us determine whether the limit of quantification has been met or not. So we don't want to set our flow rate too high or too low. We have to be within the range or at the flow rate for which they tell you. So for example, this does have a range. It says between 0.02 and 0.1 liters per minute can be used. And I'll help you determine or help you give you some tips on how to determine what is the best flow rate. Some methods, so for example for silica, only have one flow rate. So let's take a look at that example now. So here I've pulled up the method for sampling for silica, crystalline silica. And you can see it tells me that I need my sampler should be a cyclone and a filter. And I can use a nylon cyclone, an HD cyclone, or an aluminum cyclone. And no matter which one of those cyclones that I use, I'll need a 5 micrometer PVC membrane filter to put inside of my filter cassette. And here we have our flow rate is based on what type of cyclone we need. So in our aluminum cyclone, it'll be at 2.5 liters per minute. That's what I'll set my pump to. It'll draw air over that media. Or for a nylon cyclone, I'll set it at 1.7 liters per minute. But I have to be careful how many minutes I run for. If I run too long, I'll collect too much air. So my maximum sample volume that I can collect is only 1,000 liters for this method. And if I run too short of a period of time, I won't pull enough air and I won't pull in 400 liters. And so we'll look at that a little bit more from just helping you understand the method. It also tells us how many blanks we would have. So here we can take a look at yet another method. This is used to sample for asbestos with the analytical technique being microscopy, transmission electron microscopy, or TEM. And here you can see there's a variable flow rate. from 0.5 liters per minute all the way up to 16 liters per minute. And based on how long we're going to sample for, we need to meet our minimum and our maximum sample volume. We can set our flow rate or our liters per minute. And this also shows again your sampler, which would be a 0.45 to 1.2 micron cellulose ester membrane filter, and that would be placed inside a 25 millimeter diameter. Those cassettes are black and they have a conductive cowl on them, so they create the appropriate type of static electricity. So our sampling method also gives us the accuracy. This is the limit of quantification, that between 2,270 and 10,000 parts per million, the lab will be accurate in being able to quantify or measure how much material is present on your sampling media. It also tells you how many blanks will be needed. Generally, there are at least 2 field blanks per sampling campaign, or up to 10% of your samples. So let's say we were using this sampling method and we wanted to collect 3 samples for the 8-hour shift. And that means 3 samples over the 8-hour shift. We'd sample for 2.5 hours each. So we want to collect multiple points, right? So we're going to go from 8 a.m. to 10:30, 10:30 to 1 to 3, 1 to 3:30, 3:30 to the end of the day, right? We want to have multiple samples over our 8-hour shift. So what should our flow rate be, and what are the complete number of samples that we would need to be able to ensure accuracy? So we definitely would need our 3 samples that we're going to collect, plus 2 more, making it 5. And so now let's do a little bit of math to be able to solve for what our flow rate would be. So our flow rate is set between 0.01 and 0.2 liters per minute. And our minimum sample volume is 0.5 liters, and our maximum sample volume is 2.5 liters. And so the question is, what flow rate should we use? Okay, so I have the variables in our sampling protocol set up. For our method, we can run as slow as 0.01 liters per minute or as high as 0.2 liters per minute. We need to pull at least 0.5 liters of air, but no more than 2.5 liters per air per sample, or we're going to be outside the capabilities of the analytical method to accurately detect what is in the air. Because of our sampling protocol, we just chose we'd like to run for 160 minutes. So we'll use our formula Q, which is flow equals volume over time, because that's what liters per minute is. Flow rate equals volume over time. So we don't know what our flow rate is going to be, but we know we need at least 0.5 liters per air pulled over our 160 minutes. So when we do the math and we take 0.5 divided by 160, at 0.0031 liters per minute for 160 minutes, we'll pull 0.5 liters of air. This is below our flow rate, so we know we need to be up higher than that. So what's our maximum volume? Our maximum volume is 2.5 liters, maximum volume from our method, over 160 minutes. So if we set our pump at 0.0156 liters per minute, we run for 160 minutes, we'll pull 2.5 liters of air. 2.5 liters for air is our maximum volume, so we didn't go over our volume. If we pulled our maximum volume, we'll of course pull our minimum volume, and this flow rate is within our method. Therefore, we can sample for 160 minutes and take 3 samples over our 8-hour period. And this is how we used our flow rate, low end and high end, as well as our minimum and maximum volume to figure out what our actual flow rate would be given our sampling time. Now we can look at this in one other way if we'd like to. Look at our problem one more time using to manipulate our variables. Let's say we wanted to run a sample for 480 minutes. Are we able to set our flow rate such that we can do that we can run one sample? Well, Q equals V over T, and our maximum sample volume is 2.5 liters for 480 minutes. The only way to take one continuous sample for 480 minutes would be to set our sample volume, to set our flow rate, our sampling pump, at 0.0052 liters per minute. And you can see it's too low, right? So it will not be within our analytical method. Well then, what's the maximum amount of time that we can run for? Well, we can figure that out too. So our minimum sample flow rate is 0.01 liters per minute. This is our lowest flow. We don't want to exceed 2.5 liters per minute. And now we're going to solve for time. Using the minimum flow rate, if we sample for 250 minutes, we will not exceed our sample volume. Well, what if we want to use our highest flow rate? We want to make sure we have enough material on our filter. Well, we can solve for that too. So using our maximum flow rate and our maximum sample volume, how long can we sample for? We can sample for 12 minutes. So we need to set up our sampling protocol based on the amount of time that we would like to sample for, the minimum and the maximum flow rate, make sure we're in between that, and we're within our minimum and our maximum sample volume. So the next two concepts that we can see are our analytical method, and it is written different ways depending on the method. They're not all consistent, and I don't mean to laugh, but it's what makes them somewhat confusing is the inconsistency in which they're written. But the range, and this one shows between 0.1 and 1.2 micrograms per sample. This is the method's accuracy or the limit of quantification. This is the lowest that the method can repeatedly measure. That's the limit of quantification. And that differs from the limit of detection. The limit of detection here is 0.03 micrograms per sample. And that means that the analytical method, the machine that's doing the analysis, or the human, can detect a sample as light as 0.03 micrograms per sample. They can detect it, but they can't measure it accurately. It can be measured accurately within the range or the limit of quantification. So it can be measured accurately between 1 and 1.2 micrograms per sample. And these are important concepts because some folks like to use data that's below the limit of detection or the limit of quantification when they are doing their industrial hygiene calculations, when they're calculating a time-weighted average. And the risk there is quite large, in which you are saying something is there in which it is not, or you're saying it's there at a low level, when in truth it simply cannot be accurately measured, limit of quantification, or accurately detected, limit of detection. And there is a really good chapter in our text, A Strategy for Assessing and Managing Occupational Exposures. And I'll also post that chapter, which talks about the treatment of censored data. And censored data is just that, data that's below the limit of detection or the limit of quantification. And so later on in the course, we'll learn some other calculations that we can do to ensure that we collect enough air, that we have a great enough sample volume to meet that limit of quantification. And there are links here that are on the website, and there are links here that are on the slide, and I'll be sure to post those so you can just click on them, because I know you can't click on these links. I'm sorry for that. So here is your definition again of the limit of quantification and the limit of detection. The limit of detection is typically 10 standard deviations from your blank sample, and it is the lowest quantity of a substance that can be reliably measured. The limit of detection, on the other hand, is the lowest quantity of a substance that can be distinguished from your background substance. So we know it's there, but we really can't measure it accurately, and that is the limit of detection. The limit of detection is generally 3 standard deviations away from your blank. And depending on your lab results, limits below the limit of detection are noted as zeros. So we never say in our report that nothing was detected, and we don't say in our reports that nothing was present in the air. We can say that nothing was detected based on our analytical methods, and those are certainly 2 different statements. So I have a OSHA response letter here on limit of quantification and limit of detection, and I thought I'd put that in there for you to read so that you understand what OSHA is looking for. Although I know we're building our industrial hygiene programs beyond compliance, it's nice to have the interpretation from the experts. Concentrations below the detection limit are non-detect. Other values above that are reported and analyzed. There is no special requirement for results between the limit of detection and the limit of quantification, and usually they should be marked as 0 or non-detect in your results. If you're going to include them once again in your industrial hygiene calculations, be sure that you read the... Okay, let's do another time-weighted average calculation. And then a conversion. So I have the time times my concentration from the lab. So this will give me parts per million minutes, 120 times 0.35. I'm just multiplying. And I just threw my blanks in there. You would have filled out a sample volume or a time and sent that to the lab, but of course it should come back, hopefully non-detect. When I summed all this, I got my sum of time. So let's sum my sum of concentration. So my actual time-weighted average is the sum of concentration times time over the sum of time. So my sum of concentration times time is 262.6, and then my time will cancel out, so I'll be left with parts per million, divided over 500, gave me 0.5252 parts per million. And so if I want to convert this into milligrams per meters cubed, I can use our formula. Parts per million equals milligrams per meters cubed, assuming standard temperature and pressure. I can use 24.45 as my constant, and then I got my molecular weight. So I had 0.5252 parts per million equals some value, milligrams per meters cubed, times 24.45 divided by the molecular weight, which I looked up. And now I just need to solve for my unknown variable. .64 milligrams per meters cubed. Okay, had to check that one out. So assuming normal temperature and pressure, we're able to convert from parts per million to milligrams per meters cubed. So analytical methods are our cookbook. They must be followed verbatim to ensure we have the minimum error in our sample collection, because there is error built into all that we do. A sampling protocol guards against errors, so we have to have our method understood at first as we're setting up our protocol to ensure that our time periods for which we select to sample for, as well as our flow rates, are accurate. So I pulled up some analytical results so you can take a look at what they look like if you have not seen them before. We sampled and we used one sample but ran two methods on it, which you can do when the methodology of sampling is the same. They just first they weighed respirable dust, and then they broke the sample down into the different types of silica, so we can run two different methods on one sample. And so you can see here we had 0.12 milligrams per sample. And then when we take our 0.12 milligrams and we divide it by our sample volume, we had actually 0.098 milligrams per sample volume. Now down here for our quartz, our limit of detection was 0.01, and this parentheses here tells us something. So if we scroll down to the bottom of our method, you can see that the parentheses tells us that the test results is between the limit of detection and the limit of quantification and has a higher analytical uncertainty associated with it, so that these results should be treated with caution. And you also can see the reporting limit, which is listed as your RL. So we wouldn't report any samples that are below 0.02 here, our reporting limit, as well as our reporting limit. And here are samples. Oops, sorry, that was up here. There we go. This is the one we were looking at. So our samples here are unreliable because they're between the limit of detection and the limit of quantification. And you can see that they are between our reporting limit and our limit of detection. And so we'd be very careful in the interpretation of these results, although we can use our interpretation of our respirable results, which we saw again here, but here we had good results. So we had 0.15 milligrams per meters cubed with 16% quartz, and we would compare that after looking at our standard analytical errors and running some confidence intervals with the current occupational exposure limit for quartz silica.